My name is Jonathan Tippett. I'm the founder, CTO, CEO, and chief test pilot at Exosapien Technologies. We're an engineering R&D company based in Vancouver, Canada. And I think probably the best way to describe the technology that we're developing is to show a short video. So we've prepared an introductory video that shows the technology we're building and explores the motivations a little.
Have you ever wondered what it would feel like to pilot a giant exosuit? Well, so have we. So we built one. And we didn't just build one. We built the largest four-legged exoskeleton on the planet.
This is a depiction of the original vision for the project. It was conceived originally as a sport. You know, this machine was created to create a new human experience for the pilots inside. The original prototype leg we call the alpha leg, that was shot about 10 years ago, was developed prior to the formation of the company. In 2016, we got our first investors and allowed us to build this first prototype, which we have subjected to extensive crash testing and pilot training. One of the interesting things about this project is that this is in some ways our programming environment, because the machine is a human-in-the-loop control system. The machine has no autonomy, no balance, no gyros, no ability to censor or control its own movements. The implementation of CODESYS and the software and the machine is purely aimed at creating an authentic, high-fidelity experience for the pilot. That was kind of the biggest challenge in the development of this technology. And what we found in the process of training pilots and developing the motion control technology is that the machine actually has a lot of utility beyond the original application for sports and recreation. Here's an image of us out in the desert. We took it out to the Mojave Desert several times for testing and for filming and for pilot training. And you can see that I'm literally learning how to walk in this video. This is a couple of years old, and I have individual control over each of the legs on this machine, which we outline a little bit more detail in a later video. But that's been one of the most interesting challenges with developing this technology, because some of the conventional hydraulic solutions and conventional control solutions didn't give the kind of pilot feel that we were looking for. You know, in excavating and construction and materials handling equipment, precision is sort of the paramount parameter that you're aiming for. But when you're building a machine that's directly controlled by a human, and the human is in the loop and can feel the momentum and the kinematics of the machine, what you're really aiming for is a connection between the pilot and the machine. And that creates some interesting relationships between the programmers and the pilots, because the programmers kind of need to be pilots as well. Fortunately, our VP of Engineering, who's going to get a little more into the details, Curtis Perrin here, is also a pilot and a mountain biker himself. So having that integration between the programming of the human brain and the programming of the software is crucial to development. This particular test session was probably the longest distance we've ever covered. You can see mech tracks there that probably extended for kilometers. We were out there for a couple of days. It was really an incredible milestone in the development of the technology. Now, one of the challenges to testing and developing this kind of equipment is moving it around. So we thought we'd share this little video that kind of illustrates the solution that we found. We have this large black semi-truck, which is our mobile engineering test platform. It has integrated into it, it's got a small machine shop, it's got welding bays, it's got this 10,000-pound lift gate, and the pilot has to carefully sit themselves down on the dolly, and then I have to actually climb up onto the lift gate using the dexterity of the machine. So at every step of the way, the pilot is integral to the development process of the technology, whether it's the programming or just the handling of the actual hardware. This is something that a lot of people don't believe when they see the semi-truck pull up. We've got to pull a few pieces off. You can see we've pulled the bumper bars off the front, and we pulled the feet off, and then we pull it in sideways. There's literally about 15 millimeters of clearance on all three sides of the machine as it goes in there. Then you load the last few pieces in. So you know, it speaks to the amount of sort of effort that we've had to go to get this thing beyond the lab. You know, simulation has been vital, and the engineering work that we've done has set us on the right path. But really, this machine has been in the field for almost 5 years now, and we've learned an incredible amount from a controls perspective and from a hardware perspective. So we're really excited to sort of explore what comes next. Now, this next video here gives you a bit of a sense of some of the discoveries that we've made during that testing. Like I said, the original intention was as a sort of a competitive sport, and the context that we see there is giant obstacle courses, sort of like American Ninja Warrior meets BattleBots. You know, you could have multiple machines on the course. You could have them going shoulder to shoulder. You could have sort of puzzles to solve, objects to move, obstacles to overcome. So this was some of the testing that we did. What we found is that just moving the machine around, just like operating the machine in rough terrain, is a good enough challenge. But when you start getting into situations where you have to manipulate external objects, you start to really challenge the balancing aspect of it. And so this drove home the need to develop really high fidelity, high responsive control system. And that drove development not only in the pilot exoframe, but when the pilot exoframe, because the pilot is sort of connected to the machine using an exoskeletal interface, the exoframe became more sensitive, and that drove needs for the software to become more sophisticated and the controllers to become more powerful. So you'll see in this video I'm really just trying to sort of experiment with what the machine is capable of. I should note that this car was slated for the crusher. It was, all the fluids were drained. We've got a lot of feedback on this video, in particular from people who own that model and make of car, which was previously in pretty good shape until we started on it. But it was slated for scrap metal anyway, so we can't be faulted for removing a perfectly good car from the ecosystem. My foot actually got stuck here, which was something that kind of highlights the value of having a human in the loop and having the creativity of the pilot amplified through the control system. You know, if this was an automated walking machine, perhaps through machine learning you could achieve a more fluid gait more rapidly than training a human pilot. But when you get into a pickle and you're trying to use creativity to solve problems, there's nothing that beats a human in the loop, which again creates an interesting relationship between the machine, the programmer, and the pilot. That was just me saying how the car felt like a toy underfoot. It was really incredible. And this is how we move the machine for smaller deployments. We have this flatbed trailer, and climbing on and off board was, put the sound on for this, because this is a good explanation of how the control system works, which will give some good context.
And we were flipping, dragging, and crushing old cars. It was awesome. Check out the episode if you missed it. One of the biggest questions we got from that video was how we achieve such fluid motion of the machine, and how is the machine actually controlled? Well, that's the best part. The machine's movements are controlled entirely by the pilot's movements. That's what makes it a sport. So we're going to give you a sneak peek into the cockpit and give you the basics of what it takes to pilot a sportsman. The reason the machine moves so smoothly, even though it weighs 9,000 pounds, is because we've developed a technology that connects the human pilot to the machine in a way that's never been done before. So we're leveraging the skill and the nervous system of the pilot itself to make the machine move, balance, and perform. Central to this control system is the full-body exoskeletal interface at the heart of the machine that the pilot straps themselves into. It connects their arms and legs to the 4 legs of the machine and provides real-time positional and force feedback to the pilot. So you can feel the weight shift in the machine, you can feel the weight on each foot, and when the foot hits resistance, the pilot feels that resistance. And if the foot gets stuck, the pilot gets stuck. In fact, until the machine gets powered on, the pilot can't move at all. They're totally locked in there. So let's climb up into the cockpit and we'll show you how the pilot connects to the interface. It's a bit of a tight squeeze getting in, but once you're in, it's actually quite comfortable. You're locked in by your hands, your elbows, your knees, and your feet. The pilot's arms control the outside legs of the machine. The interface picks up the pilot's movements and amplifies the force by about 50 times, letting them throw the 1,000-pound steel legs around like they barely even weigh 20 pounds, but still preserving the sense of momentum that they have. The inside legs of the machine are controlled by the legs of the pilot. All 4 legs on the machine are identical, and they're on a common axis, so the machine doesn't really have front legs or back legs, it just has inside legs or outside legs. So once you're connected in all these places, all you gotta do is stand up. What do you want to do, Bubs?
I want to spin a wheel.
Well, hopefully that gives you some sense of what it is that we're trying to accomplish and some of the challenges, some of the technical challenges that have come out of that process. This is a good opportunity to introduce Curtis Perrin, our VP of Engineering, who's been kind of front and center, boots on the ground, if you will, for making the ideas that we have actually work and be implemented in reality. So.
Hi, everybody. Yeah, as John said, I'm CODESYS. I've been working for the project now for just over 2 years. Been with John out in the desert testing, as he alluded to. There's been some extreme programming environments that we've been in. Having to fix the machine or update code in some relatively inhospitable conditions. But yeah, just to give an overview of sort of the history of the project in terms of our control system and where we're at now, and then where we're looking to go actually with potentially with the use of CODESYS. So originally, when the machine was built came out of the lab in 2017, the controllers we were using were from a company called Hydroforce. They were the ECU 0809s. It's a 32-bit CPU, 100 megahertz processor, and that was all done using block programming, also with CODESYS on the back end. And then, as John was saying, we've really been pushing the fidelity and responsiveness aspect of it, as well as adding more I/O. So last year, we made the switch to a different company, HYDAC, and they're using their 540 controller. So that's our main control device within the machine. It's got 28 PWM outputs with current measurement, 96 configurable IOs. So yeah, we have lots of devices. We've added a lot of more sensing awareness on the machine that we can factor into the control algorithms. That's a 32-bit CPU, 180 megahertz dual core processor, so quite a bit faster. It also has 4 CAN networks, which allows more interconnectivity within the machine. And one of the main things that we actually added as well is the HYDAC Vision 312 Plus touchscreen display. So we upgraded the pilot console, so the main interface device you use when you're piloting the mech. And as you can imagine, with your arms and legs strapped in, and looking forward to where you're going, having a nice big touchscreen. So that's actually a over 12-inch display, 1280 by 800 pixels. So big display. We've added some tactile input on the side using some custom CAN devices. And it's a 32-bit, 1 gigahertz quad-core processor, so quite responsive. So yeah, as you're piloting, you're able to look down, see things like pressure, temperature, battery voltage, and that all ties into our connectivity with the other devices on the machine. So the motor controllers, our battery management system, and we have a number of custom PCBs that we've used that are communicating with both of the HYDAC devices over CAN to kind of bring this whole network in. And so that's kind of where we're at right now. And then this year, leaving the lab, we're really looking to expand on our data acquisition. So, we've worked through many issues, problems, and tweaks and changes, and kind of have gotten to a really stage where we need a little bit more fidelity in terms of the data acquisition to make these engineering decisions. So we're looking to implement a custom DAC using a Linux-based computer. It's going to be connected to all 4 CAN networks, adding in modules that are going to measure temperature, pressure, position, a number of other variables, and then looking to expand into an Internet of Things type environment with that connected over Wi-Fi or cell network to the cloud. Allowing, as you can imagine, it's a little hard to see real time as a ground crew exactly what's going on in the machine. I chased it along with the extra long USB cord or whatever, but it gets a little dicey. So having that wireless connection is going to really help with diagnosing issues and identifying exactly what's going on in some of these scenarios, because as you can imagine, there's many things in the moving all at once, and it becomes a little chaotic. So having that level of depth and visibility into the specific, and to be able to play it back and review exactly what happened, I think is going to really take us to our next level of controls and programming. Yeah, I think that's pretty much all I had to say. I mean, the new HIAC devices, we've switched to a structured text model for implementing a few different custom algorithms and things, and yeah, looking to expand and continue to develop our usage of CODESYS and in those devices and that connectivity. So I think with that, I bring John back on.
Yeah, so we have a little treat for our viewing audience today. We're actually in the lab. I'm going to switch. Chris, do you have to switch me to this device if I want to take the participants on a tour of the lab? If we just
start.
Yeah, just mute this instance. Sorry. Okay, and then we go like this. It's not letting me switch cameras. Oh no, that's that one. So this is the actual machine we have here. Oh. All right, so you guys are going to actually get a sneak peek at a major modification that we are doing right now. Probably is worth mentioning that all of the videos, I'm not sure how well it was streaming, but all of those videos are available on our YouTube. If you just search Exosapien Technologies, you'll be able to watch pretty much all of that footage. Now you'll notice here that these two legs are identical, and they're in an identical position. You've got this sort of knee here and that knee up there. These legs bend forwards like your elbows do, which was an engineering decision that we made based on testing of the prototype leg, the alpha leg. We found that it was much easier for it to jump in one direction than the other, so we positioned the legs accordingly. But once we got all four legs on the machine and we put a human in there and we started piloting it, we found that the ergonomics of having the inside legs, which are controlled by your legs, reversed from your natural ergonomics, was actually quite challenging. So what we've done here is we've flipped the inside legs. The outside leg is oriented that way, and the inside leg is backwards. Or I suppose you could say the inside leg is now correct, depending on what your reference is. So this machine is obviously up on blocks at the moment. It's slated to come out of the lab again in the spring. So if you want to follow along in our journey, in our efforts to implement this new configuration and bring online some of the more advanced features of CODESYS, like Curtis was saying, some of the IoT stuff and data harvesting, and a much richer interface for the pilot. We're going to be sharing all of that with our audiences on social media, and we welcome opportunities to invite other technology partners to join us as we develop the next generation of MechSuit, which is happening over the next 18 to 24 months. So we're in a design phase, and we're looking for hydraulics partners, controllers, materials, any industry that you think might be well represented on a sport of the future like this. So we appreciate having a chance to share this with the CODESYS audience, Chris.